Well, Chandra was really fascinated by black holes, as was all again mentioned by Professor Dyson this morning, and also gravitational waves and the mathematical interplay between black holes and gravitational waves. And in the last 10 years or so of his technical work, he devoted himself to these problems. Occasionally, he would get stuck conceptually about these problems. And each time this happened, he would make a trip to Oxford to talk to Roger Penrose just for a few hours. And then he would come back. And on a couple of times, he would tell us about, I was a student at that time, or a postdoc, and he would tell us about, what happened and how it was great and how much he learned and so on. So we're very fortunate to have Roger with us today to tell us about the mathematical aspects of black holes and colliding gravitational waves. Roger.
I'm also going to take a little bit of liberty with the title of this talk. Although I've been talking about mathematical ideas and black holes and colliding waves, and the reason I think that Chandra was presumably interested in the colliding waves was to do with the singularities. And this really is a legacy of his early work, the fact that black holes seem to arise, at least that's the legacy also, the fact that black holes arise from the early work he did on the boat coming to England from India, and showing that there wasn't a stable configuration for stars if they were too massive. And this talk, as I say, will be mainly more about the singularities, because I think that's where he was driving. When he was interested in the colliding waves, I think he was interested in what kinds of singularities can arise and what structure do they have, and that's sort of where he was driven in this whole discussion. Well, I have a slide here too, and I should apologize in various ways. One of them being this is out of focus. There we are. But when it comes to historical questions, I'm sure I'm liable to get the dates wrong. I don't even remember whether this was 30 or 29 here, so I hope that doesn't matter. But I will be talking about the legacy, and that is to say the singularities which one seems to be forced into. First of all, the black holes, which was where this original discussion led, and then the singularities inside them, which seemed to be what was troubling him when he went on to consider the colliding waves. And there is this very modest remark that Chandra made. I'm not sure I have the wording right even here, but it's something like this. One is left speculating on other possibilities. And you see, Chandra wouldn't put down his speculations. He probably had several, but he wouldn't. That's not the kind of thing he would have put in the paper, his actual speculations. Eddington, on the other hand, said a lot more. I felt driven to the conclusion that this was almost a reductio ad absurdum. I'm sure you're familiar with this, but I'll go on with it, of the relativistic degeneracy formula. Various accidents may intervene to save the star, but I want more protection than that. I think there should be a law of nature to prevent a star from behaving in this absurd way. So you can see that Eddington, although he was wrong in that he was rejecting this fundamental equation, the relativistic degeneracy formula, he evidently saw something which was the terrible things that were going to happen if you accepted it. And I think there is some element, even though I would have to side with Chandra in all this discussion here, even though that there is something in Eddington's realization here, I think, which is important, that there is something big here. And maybe you have to change all the physics or something like that, but at least there's an appreciation of the magnitude of the issue. Now, when I talk about things like the mathematics of black holes and colliding waves and all that, I feel sort of out of my depth. This is because the kind of mathematics that Chandra was good at is very different from the kind of mathematics that I'm good at. So I think perhaps it relates to your discussion there. There are perhaps some things when he felt he didn't quite have the full picture, he needed to come and consult somebody. The first time was actually not all across the Atlantic, was only down to Houston, Texas. That's bad enough, you might think. But you see, of course you all know about Chandra's work, but I thought I would just take completely randomly a page You see, you get the feeling for what you see in his writings. And of course another one, you can keep doing that. I'm sure that these particular pages I'm choosing would not have had any significance. They were essentially random, except I wanted something looking a bit complicated, that was about all. And I think we do need a bit of focusing to get the details up there, but perhaps that doesn't matter. But that kind of thing, you see, Chandra had a way, not just calculational, I think he could appreciate, and by the aesthetics of equations, and somehow there was some quality he had, which, okay, I could see something of it, and I could appreciate something of it, but from a distance. It's not something that I could really get into. Occasionally you would find a diagram in Chandra's, this is to do with colliding waves. This diagram actually is taken from one of my papers originally, I suppose, or not quite the way he did it. But so he did like to use diagrams when it illustrated things. This is the colliding waves. You see this is the space-time diagram. This is one wave and that's the other wave. And you will see here there's a singularity up there, but there is also a singularity, a little bit more modest one, because it hasn't got the wiggly line here, going down these sides here. And you might find that a little bit strange, because what's the singularity doing out here and out here? So I thought I'd first of all just say something about that. It's probably easier, is it? I'm not sure which is easier. But let me try and explain that singularity. So I'll do that over here. I think I'll move everything down there. And I have here written expressed with another dimension here. So we see that's not what I mean. I mean this way up, don't I? What do I mean? Oh, that's right. I see what's gone wrong. Yeah. Here we are. Here we have three-dimensional. Well, you could have to imagine it's 4 dimensions, of course. Time going up this way, and these two waves, the three-dimensional pictures at the bottom, coming together. Also, you can see something of the symmetries here, because you can slide these planes. These are plane waves in the old sense. I think they're called PP waves after eventually, but they have a symmetry of translation. And since both waves have this symmetry of translation, 2 killing vectors commuting, then you can tell the whole picture will have 2 commuting killing vectors. That just follows generally. But this is now what happens in just ordinary Minkowski space, and you just draw the picture of 2 waves coming together. So what I want to do, first of all, is turn one of these waves into a gravitational wave. So I'll take the top off, and let's make that a gravitational wave here. It's the one going off to the right. I get worried about which is the right and which is the left when I'm looking down here, but it's the one going off that way. This one, which is now an impulsive gravitational wave. Now we think of that then as cutting the space-time into 2, and that's why I've drawn 2 lines here, and then you glue them back together again, but so that it's shunted along. So this orange line here, which is straight on the underside, has to be glued with this parabola here on the over. I had to throw one dimension away here, I'm afraid, in order to draw the whole picture. And now the one I've included in these plane waves, you'll have one dimension in which the focusing is inwards and another one which is outwards. Well, the inwards one essentially dominates, so that's the important one for this picture. So that's what I've drawn, is the one where the thing goes in, and the shunt would go the other way for the going out one. And so here we have this gravitational wave has now taken this geometrical plane and focused it into this light cone. And you will see that the wave is curled up until it comes right up here. So if this wave did in fact have some curvature in it, then that curvature would all be squashed up along that line there. And that's the reason for the singularity up there. Now, of course, if they're both gravitational waves, then we have to try and draw that. So I have a picture here, and this is basically the one you're seeing over there, with a couple of dimensions thrown away. I've only thrown one away here, and each one now is supposed to be distorting the other one, and then there's no reason to believe the space up here will be flat anymore. In fact, it's not going to be flat, and that's the one that you need to have to work out and see what the space-time is. So that's what basically Chandra was concerned with here, and looking at various cases where you had fluids and electromagnetic fields and all sorts of things like that. I'll come back to some of these questions shortly, but in this case you see there is a singularity which is in fact essentially space-like, and there is an important issue that I think Chandra was interested here in, which is to what extent do you expect to find singularities which are space-like or something else. And that's an important issue. It's in fact essentially the thing referred to as strong cosmic censorship, which will play some roles in other things I want to say here. Now, just a general remark about solutions of this nature. As I said, they have two symmetries, two commuting symmetries, so it's two killing vectors, and there is a whole body of understanding for spacetimes with two commuting killing vectors, and I'm not going to say much about it. Perhaps I should have been spending my talk entirely on this or something, but I really am not going to. Chandra did consider a lot of these things here. You have both the colliding waves, you have two commuting symmetries. I think my picture sort of came apart a little bit here, so let me put it back again. There we are. And you have two commuting symmetries if you have a stationary axisymmetric configuration, maybe a black hole, and such as the Kerr solution, and you again have two commuting symmetries. And there's a lot of work on that, starting from things like Weil and Levi-Civita, and the Ernst equation, and things like the Ailes transformation, that's leading to the Geroch group. And at the bottom, just to show you the sort of thing that you're probably glad I'm not going to talk about, there is a twistor construction for all these interesting solutions of the Einstein equations, the vacuum equations here, and where you actually have what's called a holomorphic bundle over a non-Hausdorff-Riemann space. Now that's a funny idea. You see, what you take is you take a Riemann sphere, that's an ordinary complex one-dimensional spherical space, one complex dimensional, and then you cut it into three pieces like that, and the one in the middle you double up, and so when you glue it back together again, 2 points here have to be glued to 1 point there, and 2 points here to 1 point here. It's a funny idea. Locally it's a perfectly good Riemann surface, but globally it's a very strange object, and you need this in order for this construction, and you find, this is work that Woodhouse and Mason did, you can actually encode all the information of these two commuting killing vector situations. Now, I'm not going to say any more about that. I just thought I would mention that just to show you that there is a good deal of very interesting, fascinating mathematics which comes about from these. And Chandra himself, although I don't think he ever looked at this one, he certainly understood most of these things and went into the discussions of the different ways you can transform one into the other, and the kind of relationship that you get between the colliding waves that in the parallel plane, you have two planes of polarizations being parallel, which is a thing I looked at with Kahn originally, and then there were work by Bell and Sekharich and Halil and Nukku and all sorts of other people, and you get all sorts of different solutions up in the top here, and they can have all kinds of relationships with each other, which fascinated Chandra to a very considerable degree. But let me not say more about that. And I want to say more then about the black holes. This is the colliding waves, but the black holes were the things which started it all off, of course. So let me put a familiar picture of a black hole down here. This is a space-time picture again. And of course now I'm putting the light cones in. Now, I'm sure everybody here knows about light cones, but I have another reason for putting this diagram down here, explaining what light cones are, and the fact that in special relativity they're all nicely uniform, and in general relativity somewhat all over the place, as you can see they are there. And the same rules, though, that photon world lines have to be along the cones and massive particles within the cones. Okay, so that's the light cones, which I'll try to stress the importance of later on. Now let me say a little bit about black hole stability. There's a lot of work that Chandra did on this, and looking at well, a lot of these things are special properties of the Kerr solution, which for example, he was interested in the separation of equations, and I think one of the things he took greatest pride in was the fact that the Dirac equation could be separated, I think he had a trouble with the case when there was a charge in the black hole, but this is more the case of relevance to what we find with black holes. So that there are all sorts of magical things happen with black holes, with the Kerr solution in particular. The Kerr solution has, I think Brandt Carter was the first to discover some of these conserved quantities and so on, and the Carter constant, and various other things which relate to that come about. And you have killing spinners and killing tensors and all sorts of things which give rise to very elegant mathematics, which Chandra was very taken by. And I think this was something that he had these drives, I think two quite different drives in a way, but I think it's the kind of drive that you also have very much in science, especially if you're mathematically inclined. One of them may be trying to solve some overall picture problem, and in this case I guess it's understanding what on earth's going on in this collapse to a black hole, and then the singularity which seems to be there, and what on earth it's doing and what you do with it. So that sort of overall drive, which was clearly there with Chandra, and I think he sort of took a long route, first from his early work on the collapse to a black hole, to going back to studying general relativity in a serious way, and then studying what happens with black holes, and then studying the other case of colliding waves, where you seem to get singularities arising in quite general situations as well. So there's that big problem. But on the other hand, there's the nitty-gritty. What is it that you do from day to day? And in Chandra's case, it was playing with formulae, and he had this great skill and understanding of formulae, and this was what he was able to, this great skill could be applied in trying to address this big question. So you have the overall aims that you're looking at, what you're trying to do, and then what you do from day to day, what your work is, and how you exploit whatever skills you might happen to have. So now, as I mentioned, that Chandra had this skill particularly about equations. He was also very fascinated, I think, by sort of geometrical arguments. I think he didn't feel this was something he could do himself, and I think perhaps his later work on trying to get into the mind of Newton or whatever he was doing, this was really, often I think it was Newton's great mastery of geometrical argument, which was something that fascinated Chandra. But perhaps it was something that he didn't feel so much he had himself. And there are other kinds of insights that are important for understanding black holes. And, well, there are things like the singularity theorems, which show you that the singularities are no accident, that once you have a collapse, you can express the condition that that collapse has actually taken place, that you find it's inevitable that singularities will arise based on certain general assumptions. But this issue seems to me to have some relevance also to other questions, because you can look at the stability of black holes by looking at modes and that sort of thing. I just have to see what I'm proposing to say in my next transparencies. No, that's okay. So you look at the analysis of modes, which was what Chandra was good at doing, and ultimately this is very good if you want to do something very detailed, because it gives you good calculational tools, and that's very important. But there are other kinds of insights that you get maybe from looking at geometrical topological arguments, and I say the singularity theorems are an example. But the question of stability of black holes, it seems to me that perhaps not enough attention in this whole problem has been paid to this type of general geometrical argument. When I say geometrical, I include things like sort of a general analysis that you might use for differential equations and so on. So the question I'm raising here is, suppose a black hole were unstable, what would it do? And I was worried about this. What would a black hole do if it were unstable? It seems to me the only thing that it could really do is to form a naked singularity. Now, there's nothing else I can think of. Now, that should be formalized into a theorem or something, but there's nothing else I can think of that it could do apart from forming a naked singularity. I mean, it could wiggle around for a bit, then it's still a black hole. So what could it do and turn into anything that wasn't a black hole? Well, the naked singularity seems to be about the only possibility. It has to be a naked one, not just a singularity, because if it's a singularity which is not naked, then it's part of the black hole, so that doesn't help too much. You're not really concerned in this issue about what's going on inside the black hole. All sorts of horrors are probably going on inside the black hole. But when you're talking about stability, you're not talking about that, because you're only talking about the black hole and its external region. So the question really is this one of cosmic censorship. Now, cosmic censorship, I'm referring here to what's sometimes called strong cosmic censorship, which is really a very simple kind of statement, which is that in the general case, and let's say vacuum, but you might want to include various reasonable kinds of equation of state, in the general case, singularities ought to be space-like. If they're not, if they're time-like, well, null is a sort of critical case. I'm not going to worry too much about that. But if they're time-like, that means if you got close to them, I'm not saying I recommend that, but if you got close to the singularity, that means you could see it. And if you could see it, even if you're ultimately going to be crushed by the black singularity or something, it's still a naked singularity locally. So if you want to say naked singularities don't occur in the generic case, it's really a statement like. In the generic case, time-like singularities don't occur. Now, I want to talk about a different kind of singularity now. I'm slightly deviating from the title of the talk, but perhaps not from the spirit of the talk, because I want to say something about another singularity. We know that the black holes lead us into this kind of problem, but there's also the singularity of the Big Bang. Now, the Big Bang singularity is something which, in the old days, I remember people used to say, well, if you liked the Big Bang, you weren't worried by that, then you could argue that these singularities in black holes, that's, okay, you've got to expect that because you've already got the one you like, you see. Or if it was the other way around, you might be quite happy to have these singularities there, and then you would say, well, somebody would say, well, there's nothing wrong with the Big Bang being a singularity because we've already got one here, you see. So there is this issue of, so I'll put it over here, of the Big Bang singularity. So now I've got another cartoon here. Don't worry about my picture having the spatial dimension closed up. That's just so I can draw the picture, really. There's nothing meant to prejudice whether the space-time is spatially closed, spatially open, spatially hyperbolic, or flat, or what. That's not important here. The important thing is that you have this Big Bang at the beginning, and you have the time going up the picture here, and we seem to have something which I prefer to call a cosmological constant, which tells us that this universe should be continuing in its exponential expansion indefinitely. Now, that's the sort of, you could say, a standard picture we have, apart from the fact that usually people say there's something going on down there. You wouldn't see it on this scale because it's tucked right in at the beginning, and that is inflation. Now, I should confess right at the beginning here, I'm not a supporter of inflation. I'd rather hope it's not there. Of course, it might have to be there, but if it's there, then you won't see it on this scale. So you need your magnifying glass, and with your magnifying glass, what you might see is something sort of like this. Okay, now, there's a sort of point about these two pictures, which I'm sure is often made, which they look rather like each other. So here you have an exponential expansion there and an exponential expansion there. Now that's, of course, lots of people have pointed that out. I'm going to come back to that point in a different way. So I hope I will if I don't run out of time too early. This picture is also rather incomplete in that it doesn't have the black hole singularities in, so let me put them in too. Here we have singularities arising from the collapse of matter into black holes. So this is the sort of picture that we have, singularity here and lots of them in black holes. Now, they look superficially the same perhaps, but in detail they're likely to be extremely different. And that really has to do with the second law of thermodynamics. And the second law of thermodynamics tells us that this is a nice special state and these are sort of general states. Well, that point I'll come back to as well. But for the moment, I wanted to say how the cosmic censorship, strong cosmic censorship has a relevance to this. well, it's relevant to the question about whether, for example, inflation, which we're taking is there now, if inflation were there, would it explain the uniformity of the universe? Now, this is something I always worried about. So let's suppose that inflation is there and you have the inflaton field and maybe you have some kind of processes going, phase transitions or something like that. All these would be described by a physics which is ultimately time symmetrical. Now, if it's time symmetrical, then of course that's just as good a solution. The only thing is here, now you have to worry about your second law working the other way, and so you'll have, just suppose you have the sort of irregularities that we see now, but not in such detail that if you evolve them you'd get back to the same state that we had the other way. Let's just put them in, wiggle them around a little bit, so they're still there, but not exactly organized in this teleological way that would need to get back to the Big Bang we've seen. Well, what would you expect? You'd find black holes forming, and those black holes will start to congeal, and they will form a great mess in the end. So now we have a picture which is much more like that one. Now this picture, you could have put into this picture all the physics, the inflaton field, all that time-symmetric physics in there that you put in for inflation. So let's do that. Okay, what about these things like phase transitions and so on? Well, those are all supposed to be entropic, so there's not a violation of the local physics. It's just that you use the second law of thermodynamics. Well, we can use the second law of thermodynamics here. Doesn't matter. Let's take that, and then that's certainly a possible start of the universe as well. And the question is, why wasn't it? And these, just from entropy considerations or phase space volume considerations, are by far the majority of states, by an absolutely huge factor. Now, one question you might raise here, and that is that perhaps that isn't an instantaneous event. You see, that we're accepting as an instantaneous event. Well, that's the cosmic censorship question again. The strong cosmic censorship is telling us that general singularities are going to be space-like. So if you believe that, then this will be, for all its mess, will be a space-like singularity. If it's a space-like thing, space-like boundary to your space-time, you can start drawing surfaces of equal time and so on, and there's nothing against that being the initial state to the universe. So there is a sort of role for strong cosmic censorship. I don't actually think it's a huge role, because you consider, well, even if not all states are like this, there'd be a good many of them, and so you still have the question, why don't they contribute to this possible initial state? And you could also say, suppose you have quantum gravity and so on, well, why don't these other things contribute to the state of the initial, the wave function of the initial universe or something like that? So that is a serious issue to me, and I want to say something about that shortly. But let me say something about the other way up, this way up, as I've drawn it, the remote future. Now, in the remote future, we certainly have these black holes going along, but we also have to take into consideration that, according to Stephen Hawking, you will have the black holes gradually evaporating away. So I'm accepting all that. That comes from general thermodynamic principles. I have something about the information paradox there which I don't want to worry you about. It is actually of importance to the things I would say if I had more time, but I'm not going to say them here. What we do seem to have is a collapsing material to a black hole happening all over the place, and ultimately this thing disappearing. Now, it will take a long time. Certainly for the largest black holes we know to be out there, if you think of something of 10 to the 10 solar masses, which I gather there are some out there, maybe a bit bigger, probably ultimately quite a lot bigger, they will take probably even over a googol years before they disappear. So that's 10 to the 100 years for something of the sorts of sizes that we do see. So you've got to wait a long time. And that's because the Hawking radiation coming out is still at a very cold temperature, and the universe, the microwave background, is a lot warmer than that temperature. So it's still absorbing more than it's radiating. But after a while, the universe cools down to below than the black hole's temperature, and this thing will gradually go away and disappear with a pop. This is all in accordance with the second law of thermodynamics, and so it makes a lot of sense. The pop, I'm only calling it a pop and not a bang, because, okay, it would be nasty going off in this room and it a bit like an artillery shell or something like that, but pretty small when you consider the mass of the black hole that might have been involved originally. So I don't think it's worthy of the name bang. So, okay. But of course that modifies our picture here. It's not quite like that. It's more like this. I put the words boring era up here. It was one of the things that about 5 years ago I started worrying about that series. I mean, worried about it before. But it seems to be an awful shame that our beautiful universe with all its interesting things going on should just end up with this kind of totally empty, boring thing. With the black holes, as they gradually evaporate away, it's nothing but sort of photons coming out, except the last bit. And there's not much energy in that last pop. So it's a pretty boring thing. Now, those boring kind of universes are the sort of thing that we've studied before. But let me say a remark first about the boredom. You see, it's boring, but then you could say, well, who's going to be bored by it? We're not going to be around then. And the main things that are going to be around in those days will be things like photons. And photons, it's pretty hard to bore a photon. Well, for more than one reason, but the reason that I'm interested in here is that, not that he probably doesn't have experiences, but because the very notion of time seems to be tied up with mass. And if you have essentially massless things around, it's pretty hard to build a clock, because it's basically clocks. Well, atomic and nuclear clocks ultimately depend on the relationship between Planck's and Einstein's equations, which tell you that every particle is basically a little clock. It ticks away in proportion to its mass. And of course you can't use that to build a clock very well, and you need lots of particles, but nevertheless they form the basis of the accurate clock seems to be ultimately something like this. And this means that we have to worry, when you've got mass around, about not just the light cones, but these surfaces here, which tell you what the ticks of the clocks register. So you've got the light cones together with the crowding of these equal time hyperboloids. Now, I hope I haven't lost the one transparency that I was trying to keep ready to bring back again here. And I had a lot of trouble last time I was talking about these things. Finding things, because it's always too dark over here. That's it, there we are. So, rather than describing your space-time in terms of light cones, you have to bear in mind there's just a bit more structure. You see that the light cones themselves are the ratios of the components of the metric, so you have 9 numbers per point to characterize the light cone structure. You have one more to give you the surfaces here, these hyperboloid surfaces, which actually give you the full metric. But the point I want to emphasize here, that the light cones themselves are most of the metric. This is the conformal structure, and the conformal structure gives you most of the metric. And if you want the whole metric, you put that in as well. And lots of parts of physics just need this, only need the light cone structure. Maxwell's equations are conformally invariant in the strong sense that they only need the light cones, together with the way that sources, the charges affect the Maxwell field. That's also conformally invariant. And if you take Yang-Mills equations, and if you remove the mass, then again you have something which appears to be conformally invariant. So the things which seem to respect mass, which seems to respect the metric as opposed to the conformal structure, are more things where mass comes in either as rest mass or else when you worry about general relativity. But if you just have conformal structure, then you can do interesting things. One thing you can do is to look at infinity. See, here we have a nice picture that I'm sure you're familiar with, which represents hyperbolic geometry according to what's referred to as the Poincare disk, but that's because it was presumably because it was due to Beltrami. Beltrami was the first to describe the hyperbolic plane in this way, the main point I want to bring out here is that the inhabitants of this universe, these angels and devils, they appear to crowd up onto the edge here, but if you think of the Euclidean space in which everything is embedded here, there's nothing special. You see, this is conformally related. The metric that they experience is conformally related to the Euclidean background here. So it's as a conformal picture, you could extend beyond this boundary. It makes perfectly good mathematical sense. Infinity is represented here in a conformally smooth way as a boundary. Well, that's a trick that we've been playing for a long time in relativity theory. And if you do it in the Lorentzian signature, you can talk about infinity, as long as the physics you're interested in is basically conformally invariant. And that's really what I'm trying to argue for here, where the black holes have gone off with a pop and so on. One can worry about the odd rogue electrons and things running around, but let's not worry about that for the moment. I put that down at the bottom here, but I prefer you didn't worry about that right now. We do have this picture that we've had for a long time of what we sometimes refer to as scry, or conformal infinity, which in the case of a positive cosmological constant is space-like. That's a role for the cosmological constant here, which worried me for a long time, but now, since it seems to be out there, I've grown to accept it, and having grown to accept it, I now realize that you can do lots of things with it that you couldn't do if it wasn't there. So let's accept it, and that means you can squash infinity down into this nice boundary. Okay, so we've got the boundary sitting out there at future infinity. Now, I want to talk about the other end of time, and we had this little problem with our beginning and try to say what it was that distinguished this from this. Why wasn't that great mess what started the universe off? It not just started the universe off, it started off the second law of thermodynamics, and that's the key thing. So you need something which characterizes this initial state. Now, just as a mathematical statement, I tend to use this term here, Weyl curvature hypothesis. It's just saying the same thing again, but in a mathematical language. I'm trying to say that perhaps the constraint on the Big Bang was that the gravitational degrees of freedom were not activated in the early universe. That seems to be the case. And that the good way of saying that is to say that the Weyl curvature, or the conformal curvature, which describes the free gravitational field, was in fact zero or something very limited in the early stage of the universe. But it's a sort of awkward condition to phrase mathematically, mainly because the Weyl tensor is a tensor, and if you're talking about what a tensor does at a singularity, you have to think a lot. And you have to talk about limits and things like that, which are not so nice. But Paul Todd has a very nice way of doing this, which he introduced and made a good study of it, which is to say, let's, as you can do with the standard Freeman and Robertson-Walker models, you can stretch the Big Bang out. Here I've squashed infinity down. This is the opposite. You stretch the Big Bang out and form a nice smooth surface. Now, if that is a nice smooth surface, it rules out almost all of these horrendous congealing white holes or whatever it would be that you're trying to get rid of here. So that is a very nice way of stating this Weyl curvature hypothesis. Just say that it's smooth at this, as a conformal structure, forget about the mass now, as a conformal structure, it's perfectly smooth. In fact, there's some physical rationale to this too. You see, it was originally just a mathematical trick, but you can say that the temperatures become so large at the Big Bang that rest masses become ignorable. So maybe it is the conformal geometry that's relevant. The rest masses you can forget about. In which case, if the particles that are sort of living around down here, to them, the Big Bang is no big deal. It's just another surface. So you might say, well, maybe they came from something behind the Big Bang. Now, I suppose you could say, well, the original thing is just this is a mathematical trick. Is this mathematical trick something which has physical content? And this is perhaps suggesting it might. Well, if there was something prior to the Big Bang, the most obvious thing I suppose one thinks of is maybe there was a collapsing phase and it just bounced out into this. That, of course, has all the problems, if you want a second law going in the usual way, that you get that great mess that I was trying to say didn't happen in the Big Bang, and now it's going to occur in the Big Crunch. So that's not going to help too much, because they don't fit together at all. However, if we go over to that picture there, something which does seem to fit is one of these against one of those. So this is the crazy idea that I've been playing with for about 5 years. And I've just written a book, which I'm afraid you can't get here just yet. It's just been published a few weeks ago in England. But it will be coming here eventually. This is the mathematical trick aspect of it. Here is the universe as we understand it. And I've not put inflation in this deliberately, although it doesn't make much difference at this stage to what I say. Stretch out the Big Bang to make a nice smooth surface. Squash down infinity to make a nice smooth surface. This infinity thing happens almost automatically. That is work that Helmut Friedrich has done, and so on and so forth. Tells us more or less the general situations. It's reasonable to say they have this nice smooth future boundary. However, the other one, the Big Bang case, that's a huge constraint. And it's the kind of constraint that maybe is what we seem to have in our universe. So I'm saying stretching out and squashing down at the other end gives you a universe which is conformally a nice smooth manifold at both ends. So the crazy scheme that I'm putting forward, or have put forward for about 5 years, is that what we think of as our universe is but one eon in an infinite succession of eons. And each one starts with its Big Bang and goes to infinity, and then forgets how big it is and becomes the Big Bang of the next eon. Forgets how big it is, of course, just a way of waving my hands around. You need a lot of equations to translate this process into something which makes sense mathematically. That can be done. I'm not going to do it here. But I'm just saying there is a way of making all the equations make sense as you get across from one eon to the next. You do have black holes, and they have their little problems in the middle. But the question I want to address now is this picture something that we could experimentally test? Can you actually see into the eon prior to ours? And I'm trying to say that if this scheme is right, you can. You can see through the Big Bang into the eon prior to ours. And what would you see? Well, I'm saying that the major events that one would see in this previous eon would be things like this. Encounters between huge black holes. So you'll have galaxies, clusters of galaxies, and they will not partake of this exponential expansion. They'll hang around as clusters for a long time, and every now and again the galaxies will run into each other. Every now and again the black holes will swallow each other up, and when that happens there will be a burst of radiation, a huge burst of radiation, which will carry away a significant proportion of the rest mass of those huge black holes. So we've got to think of an absolutely violent event here, and on this kind of squashed up scale, you see, I've drawn the join between one eon and the next here is just a line, but of course that's a three-dimensional surface, and in this picture I've done a little better by drawing it as a two-dimensional surface, but you've got to bear in mind this is really a three-dimensional surface. And there's us up here looking back at whatever these great bursts of gravitational radiation will do to the initial material in the universe here, which I take to be some initial form of dark matter. And as this gravitational radiation comes out, it will give it a kick. Now that kick will either be for distant black hole encounters towards us, in which case you might think it was a bit hotter, or it will be away from us, in which case it might be a bit cooler. But the other thing is that although there might be a lot of detailed structure in this wave, and it would be very interesting to know, because here is another role. If this scheme is right, we have a completely new role for all this work that people have done on working out encounters between black holes. Of course, on the sort of immediate scale, you're only looking at things which are effectively delta functions, because the time scale here will be very, very tiny with regard to what we can see up here. So it will be more or less like an instantaneous event. But there may be details that could ultimately be picked out, if you could see this at all, of course. Now, the claim then is it's a bit like ripples on the pond, where you have encounters between black holes showing up as these ripples. And the question is there any evidence for this in the cosmic microwave background? Well, about 2 years ago, I was visiting Princeton, and I asked David Spergel, and I said, is there any evidence for this? And his response was, well, I said, has anybody ever seen this? And he said, no, nobody's ever seen that. But then nobody's ever looked. So he then said he'd look at it himself, maybe, if he had time, and he'd get a colleague, Amir Hajian, who was working there, and eventually he did give it to him. But what they did eventually was somewhat inconclusive. And I want to tell you about something else, which I only learnt about last week. So it's got all its question marks. It's very provisional, what I say. It might be something that will show that what I'm showing you is not right for some reason. But let me tell you what the situation I've been presented with last Monday. I mentioned this kind of thing to a colleague, Vahe Gazadjian, who works in Armenia. And I was only initially interested because the previous analysis that had been done in Princeton seemed to come up against problems of possible distortions in that there may be large mass irregularities, which would mean that the circles that you seem to see, this analogy with the pond is not unreasonable, because what you actually see is the intersection of these cones and so on, and what you would see is a circle. But that's assuming that there are no distortions between this and us, and so the circles may get a little distorted. But Gazadjian had been looking at possibly measuring some of these distortions. But I saw him on Monday, and he said he'd found some interesting things here. What he'd done, it's sort of almost the other way around from what the people in Princeton had done. What they'd done would be to choose an angular radius for the possible circle, and then look all over the sky to see if there was any departure from Gaussianity in the average temperature over the circle. What Gazadjian was doing was to look at individual points on the sky and circles of different radius with those centers, and then not averaging to find the average temperature, but he knew that as well, but instead to look at the variance over the circle. So the idea would be, although this isn't what I told him, but it seems these impulses here that you would get in this picture would be things which are pretty uniform all over the whole disk. Okay, there might be bits of irregularities, but it's a great impulse. The major effect is over that thing there. And this will hit the initial matter and give it a kick. And although I still have a little bit of a problem understanding how to view this, the view seemed to be, his view anyway, where it was, that you would expect to see much less variance on these circles. So he was looking at different circles and seeing where the circles, what the variance was for different possible positions in different radii, and with a certain width of circle, so that the ellipticity introduced in the R eon might be not troublesome. And he found pictures like this. So this is, the variance is going up, and these are different radii. So there's increasing radius here, and he said you'd get these, he's got these spikes here which might mean something. So I said, well, if you see one of these things, you won't really see several of them, because if they are black hole events, that black hole is not going to go away. Okay, it may get a kick like the one you say, but that's pretty small on the scheme of things. So it's pretty well going to stay put. So that the next time it swallows something else, that there will be another circle with the same center. So for fixing the center and looking at different radii, you ought to see, if you see one instance, you ought to see several. And indeed, that's what he finds. He's found, out of looking at, let's see, I think it was 12,000 different points on the sky, and avoiding the galactic plane and things like that, 12,000 different points on the sky, he found about 12 different cases where there was a spike. And every time where he found one spike, he found several. So here's, I should say, first of all, what does it look like if you just take Gaussian input and see what happens? Well, this is what it looks like. There should be some more stuff on the top. I asked him what all this stuff is doing. He said, no, everything produces lots more variance. All sorts of things can do that. Galaxies in the way and all sorts of things. But to produce less variance is the remarkable thing. So he sees that, and I only have one other to show you here, but it gives you a typical view of what you see. This one actually has 4. So you tend to see 2, 3, or 4 when you see one. Now, of course, this might be some spurious effect. And people tell me to be cautious, and indeed I'm trying to be cautious. It could well be, these are all from WMAP data, and it may be that the things they do to the data before you're allowed to look at it, and all sorts of issues might come up, and you really need to look at it in all sorts of different ways to see whether these effects are there in other ways of looking at the sky, of the CMB sky. So that's, as I say, it's only a week old, so I have no idea where this would go, whether one should believe it or not. Of course, if it's the sort of thing is encouraging your own theory, you're likely to believe it. So I'm feeling rather positively disposed towards these things, but I'm sure that won't apply to everybody. Perhaps I'll leave that one there. That's a nice one. Okay, now I want to end by just giving a bit of the geometry that's involved here. You see, if the scheme I'm talking about, which I call conformal cyclic cosmology, if it's right, our own eon is represented on a conformal picture here. A conformal diagram, so I've drawn the speed of light at 45 degrees all the time and stretched and squashed as necessary. What you find is that future infinity and the Big Bang, we're about 2/3 of the way up. This is without inflation. With no inflation, we're about 2/3 of the way up this picture. Now, if you assume that what goes on down here is what I'm just saying, these bursts, well, first of all, I'm drawing this picture. It's a bit hard to draw all the dimensions in this all at once, you see. You have to, that sphere is actually thought to be, you must imagine it going on in this Big Bang surface here. So although I've drawn it here, it's going on in there. And this is, you're choosing some angle alpha, and you're looking at a circle of that radius. Okay, so that's that picture. And what you find is that for a given circle, there is a hyperbola in the previous eon of possible sources which would give that circle. You see, you have to imagine that whatever it is that's producing this impulse, that impulse is likely to be coming out with the speed of light and hitting the last scattering surface somehow. And when it hits that, perhaps it hits the Big Bang first. I mean, I'll come back in a minute to inflation. But it's a picture something like this. And there's a hyperbola of possible points which give you a given circle. Now, you can work all this out, and it's just straightforward geometry, actually, quite a nice little exercise. You see, you can, perhaps I'll put this one over here. It's just little nice bits of Euclidean geometry. You can work out these hyperbola and where everything is. Of course, if it's one event going off several times, there will be several of these hyperbolae. And you can see where they would be. That's not difficult. But suppose this is all wrong, and inflation is really the right picture. So let's take that. First of all, that's last scattering surface. And then I've got to put inflation in the picture. And I've got to find inflation first. Where is it? It's awfully difficult to see these things. How irritating. It doesn't matter too much because it's only one straight line. Has it dropped on the floor? It's a small one. It's only one straight line, so I even can use it here, you see. The old-fashioned pre-inflation cosmologies were like that. Or a little up closer, not like that. Inflation, you have to move the Big Bang way down, right over across the other side of the lake or something. I'm not quite sure how far away. It depends on which version of inflation you take. But these hyperbolae are up here. So it would be very hard to see that if it was anything other than being just close up to the top, in other words, just at the last moment of inflation, that these events could take place. They couldn't be prior to inflation. Well, they could just be, but I think it's inconsistent because it's the very tail end of the hyperbola, and you see that the probabilities of getting things to look like this are highly, highly unlikely. So if it is inflation, it would have to be at the very last sort of stages of inflation. Of course, it might be that it's spurious, and that there's something else giving these signals, and that it's something else, and it's nothing to do with inflation, it's nothing to do with what I'm saying, it's nothing to do with physics. Well, it's something to do with the way the WMAP thing works or something. So people have got to have a look and see whether these things are still there in other ways of looking at the sky. But it seems to me, as long as it's not completely spurious, this is very exciting. And it would open up all sorts of questions. Let me just mention one, well, 2 points. Let me mention 2 points. One of them has relevance to this talk in the other way. This is a kind of curiosity. I hadn't thought about this before. But you think, suppose these things went off and 2 of them overlap, you see. So you have these ripples in the pond overlapping. That means these gravitational waves have crossed. And so you have an instance of colliding gravitational waves. And so even that piece of work that Chandra was looking at maybe would have some relevance. And the details of what goes on with colliding waves maybe would have some implications. That would be very exciting. None of the ones that Gosajian indicates seem to have any overlap, but that is at least potentially a possibility. So that would be interesting. All sorts of other questions arise. One big one is, if this picture is correct, then we have a previous eon. Were the constants of nature the same in that previous eon as they are in ours? And there are all sorts of discussions people bring up. Wheeler in particular, when he had his pictures of oscillating universes, do the constants of nature get churned around each time? And so there is a question. I'm not telling you an answer. I don't know. I have no idea. I'd prefer they didn't get changed, I have to say, because it just makes my life a lot more complicated. But the other way around, it's interesting because maybe you have a handle on this. Because if in the previous eon they were different, they would perhaps that would have implications that we would be able to see and know what these values of some of those numbers might have been in the previous eon. So that's an exciting, if perhaps rather wild, possibility. So let me leave you with that. Thank you very much.
Okay, we're quite time for some questions. So, Virginia?
Let me speak for Jeff Burbage.
Yes. Yes.
Let me speak for Jeff Burbage, thereby saving Narlicker the trouble of having to do it, because he cannot speak for himself. I think it's beautiful.
Thank you.
I also think it has a lot to do with quasi-steady state.
Yes, indeed. Yes. No, I agree. In fact, it's motivated, I think, in a kind of emotional way, because when I was getting seriously interested in cosmology, Dennis Sharma was the person I learned an awful lot from, and of course he was very wedded to steady state. Then, of course, when...
He gave up too soon.
You think he... Yeah, I keep wondering what he would have made of the scheme, yes.
Yes, next question.
Hello, it was a pleasure hearing you talk. I have a question. You referenced Weil in your talk quite a bit. I was wondering if you've read the book, I believe it's by Weil, Continuum Hypothesis.
Yes.
And I wonder if you could speak a few words on his criticism of the continuum hypothesis and how it relates to this.
Yes, but that I'm not sure how much it does relate to this. I mean, if it's the one you're referring to, I think this has to do with mathematical logic and whether one should accept. Well, there's this thing called the continuum hypothesis, which is to do with whether there's a number between the Aleph 0 and C, 2 to the Aleph 0. And this is still an unsolved problem. Well, unsolved, it's one of these funny things like logic. You can say it's unsolvable because it's not solvable by the standard methods of set theory. But then we know there are... Since Gödel, we know there are going to be things unsolvable by those methods. I don't see that it has a great relevance to this question. I mean, it does in a sort of negative sense in that, you see, there's a discrepancy between what I've been saying here and what people who do quantum gravity normally think. And that includes me, before 5 years ago, where one would always have said the Big Bang is a nice place to see quantum gravity. You see, because you have curvatures, radii of curvature of Planck scale. Surely that's a place where quantum gravity is going to make its mark. Now here, I'm saying, no, you can get away with classical equations. So I'm saying that quantum gravity, which is a place where maybe the continuum does something really wild. You see, I think that has some relation to that question. The continuum in the physical sense, and I believe that's probably right in the case of black holes, where the curvature... It's the Weyl, when you mention Weyl, it's the Weyl curvature which then goes wild. And so you get radii of Weyl curvature, which are very, very tiny and maybe Planck scale. Whereas at the Big Bang, it seems to be that the Weyl curvature is not big. It's practically zero. And so if you take the view that it's the Weyl curvature, which only when that gets large do you have to bring in quantum gravity, that's consistent with what I'm saying. But that's not the usual point of view.
Well, this goes into the question that I wanted you to speak on was whether space-time is discrete,
yes,
or whether it's continuous.
Yeah, I mean, it's the same question, but people usually say that would be done at the Planck scale, you see. That's the usual argument. And I'm saying, okay, maybe that's true. I'm not saying anything against it having kind of discreteness of some sort down at that saying, but I'm just saying that it's the Planck scale with regard to Weyl curvature, not with regard to the Ricci curvature that we seem to see in the singularity in the Big Bang. So that's where I'm sort of departing from the standard quantum gravity view, which is that it's all kinds of curvature that when they get large, you have to worry about the discrete nature, the kind of thing you might be talking. Maybe discrete, maybe all sorts of different ideas that people have about quantum gravity, non-commutative geometry, this and that. There are many, many different schemes.
Okay, so I think there's a question at the very end first. That's at the last row. No, not you. There's somebody else before you.
Dr. Penrose, in the popular press, Stephen Hawking was recently quoted regarding that I don't know if it's an accurate quote or not, that because of the law of gravity, we have an explanation of the universe being created from nothing. Are you familiar with this quote?
I know. I had to review this book for the Financial Times. It was the one thing I didn't pay any attention to because I thought that was the same thing that he'd always been saying all his life, and it didn't look to me anything new, so I didn't comment on that.
but do you sort of agree with that kind of statement?
I prefer to leave God out of this discussion. I think it's, it will just bring in arguments that I prefer not to address at this point.
Okay, so there are two questions over there. I think the gentleman in the front first. Okay.
I have a question about the nature of quantum mechanics and impacting the singularities, and where that's related to the origin of the second law of thermodynamics.
Yeah.
But what about also the possibility of invoking the third law of thermodynamics at that empty phase at the end of the universe in the conformal boundary? Would that also possibly merge when you go across the boundary with a, quote, fourth law of thermodynamics?
I can't remember which order they come in, unfortunately. No. One of them says you can't reach absolute zero temperature, but that's three, is it? I've forgotten what it says. Okay.
No. The idea there would be a maximum temperature.
Oh, maximum temperature.
A so-called fourth law of thermodynamics.
Oh, I see. Yeah, well, again, I think I don't want to comment on that. I mean, I know what you mean. Okay, I don't see the relevance very clearly to anything I've said here. Of course, maybe in black holes when all hell breaks loose, but then all hell breaks loose, so... In the black holes, yes. Yes, I've nothing against that. And that will be whatever quantum gravity is, will have something serious to say about that. It will also have something serious to say about certain other things, which I hope it will be more relevant to experiment. So I do think it's a very important subject. It's just that I've kind of been diverted from thinking that that's what you should be looking at to understand the Big Bang.
Okay, so one last question, please.
Since we have Dr. Penrose here, he could comment on this. His work was very close. His early work on spinor analysis was very close to what I did at MIT after I left the post-Newtonian. I did not follow spinor analysis. You can simply not do it mathematically with spinor analysis. It's impossible. I followed Sachs's bivector formalism that was published around the same time as spinor analysis. I put in the Lorentz, I used the Lorentz transformation, which I found in Debney's paper, put the velocities and angles, a 6-parameter thing, derived all the transformation equations for the Riemann tensor, all 14 invariants, all the Cayley-Hamilton equations.
Oh, we don't have too much time, so can you just ask your question quickly?
The question is, if the gravitational field all gravitational fields transform, under Lorentz transformations. Even the Newtonian gravitational field is not Lorentz invariant. If the gravitational fields transform into motion, general relativity is wrong.
Okay.
The only thing that might remain is the Riemann tensor.
All right. Okay. Maybe we should have one last question over here, please.
My name is Alan. I'm from Asunción, Paraguay. And I had a funny question. You mentioned topological issues, and I was wondering if perhaps in this new paradigm, any topological invariants survive transcending the eon barrier, in your opinion?
Yeah. No, the answer is not just an opinion. If the scheme is right, the topology just goes right through. So the topology of the universe is basically the same as the topology of the crossover surface, and that will simply carry through. So the picture I have is not just everything. If the universe is closed and sort of spherical topology, hyperspherical topology, that would continue. If it's Euclidean type of overall geometry, that will continue. And if it's hyperbolic, that will continue. And whatever identifications you might choose to make a closed-up version, that would continue too. So it doesn't really have anything to say about these questions.
Okay, so let's just thank Roger now. And 2 o'clock.